graphing. So this first example, determine the maximum number of real zeros, turning points, and x-intercepts the polynomial can have. So you got to be very careful with this wording. It doesn't say how many does it have. It says how many can it or could it have. So that's using the idea right above this example. Another thing to remember is that real zeros and x-intercepts are the same thing. So our x-intercepts is the same thing as our real zeros, because that is the points or locations where we do actually cross the x-axis. So the maximum number of real zeros a polynomial could have is equal to the degree. And if we look at the polynomial we are given here, the degree is 3. So that is the maximum number of real zeros we could have. For the turning points, a turning point is like where the function changes from increasing to decreasing or decreasing to increasing. So kind of like how many maximums or minimums does it have. So a function can have at most one less than the degree for turning points. So since our degree is 3, this function here can have at most 2 turning points. All right, there's your steps for graphing a polynomial if needed. Zoom, in case you need to pause it on those, there's your steps. All right, so example 2, sketch the graph of each polynomial. All right, so first thing we want to do is find the leading term, so we can do our in behavior. This one is in standard form, so we don't need to worry about rearranging anything. I'm just going to put a little label here that says in behavior. So all of this work right here is going to go with our in behavior. So here's our leading term, negative x cubed. So as far as writing your in behavior out, you don't need to write it out formally like we did in the last section, because you're just going to use this to make sure your graph is sketched correctly. So for our right end, it's based on the leading coefficient. Our leading coefficient is negative, therefore our right end is going to be down. For our left is based on the degree. The degree is odd, therefore the left has to go the opposite direction of the right. So since the right went down, our left is going to go opposite and go up. Next thing we need to do is find our x-intercepts or our zeros or our roots, whichever you'd like to call them, because they're all interchangeable. So that is where we are setting our polynomial, in this case f of x, equal to 0 and solving for x. I'm going to pull my polynomial, negative x cubed plus 2x squared plus 4x minus 8, and set it equal to 0. All right, so at this point, we're dealing with real zeros still. This is a 4-term polynomial, so your strategy for finding your roots is factor by grouping. So I'm going to put the first 2 terms in a group on their own, plus sign between. Second 2 terms going in a group of their own. And then within each group, we take out the common factor. So negative x cubed plus 2x squared, we want to take the negative out since it's on the front. And then they also have an x squared in common, which is going to leave us with 1x, and then change the sign because we took the negative out, minus 2. For second term or second group, they have a 4 in common. So I'm going to take the 4 out, and that is going to leave us with x and then minus 2. All right, each chunk has the factor x minus 2 in common, so we're going to remove that and slide together what is left, which would be negative x squared plus 4. All right, at this point, that back factor can actually be factored further, but sometimes we have a hard time seeing it when the front's negative. So I am going to take a negative out of that back group here and just slide it all the way to the front. So I'm going to take out a -1 or a negative. You can write it either way. That has no effect on the x minus 2 because I didn't remove it from that factor. It's going to change the sign on everything in this last set. So that negative x squared is now a positive x squared, and my 4 is now a -4. negative 1 is just floating on the front. We have our x minus 2. And then x squared minus 4, that is your difference of squares. So x plus 2 times x minus 2. All right, if we look at this, catch you have a factor in common. I'm going to go ahead and rewrite it using an exponent so I make sure I get my multiplicity. Order you list your factors in does not matter. I'm going to do the x minus 2 first, and since there are 2 of them, it's the whole quantity squared. And then we have our x plus 2. All right, our polynomial is completely factored, so we're going to set each factor equal to 0. So the x minus 2 gets set equal to 0, which means x is equal to positive 2, multiplicity 2, because the exponent. The negative 1 out front is a non-variable factor, so it's just ignored. Then we have our x plus 2 that we set equal to 0. I guess I don't need my parentheses there. Oops. So x equals negative 2, and its exponent was a 1, so m1. So what that means is when we hit the x-axis at 2, we're going to bounce. And when we hit the x-axis at negative 2, we're going to go straight through. All right, so we have our in behavior, we have our zeros. I now need my y-intercept. So your y-intercept. Remember, this is where x is equal to 0. So to find your y-intercept, we are plugging in 0 for x, or in other words, calculating f of 0. So if we go back up, I like to use the original form of your polynomial from one of the last couple of sections. Remember, if your polynomial is in standard form, then your y-intercept is the constant value because everything is going to 0 out. So we're just going to be left with the constant term, which is negative 8. So f of 0 is negative 8. All right, so for our graph here, I did not give you a grid. So what we're going to do is we're just going to plot these points and only these points. So I've got my x and y axis. Here's my x-axis. And here is my y-axis. So the numbers I want to see, I need to mark my y-intercept, which is at negative 8. So I'm going to come down here. I'm going to call this negative 8. And we know we hit the y-intercept, so I'm going to go ahead and put a closed circle here. We hit our x-intercepts or zeros at negative and positive 2. So I'm going to call this negative 2 and go out about the same distance. Positive 2, also both getting closed circles. For our in behavior, I want to go make sure I go the right direction. So my right is supposed to be down and my left is supposed to be up. So my right side, I'm going to come out here out of the graph and put a down arrow. For my left side, out of the graph and put an up arrow. All right, so we know our graph has to be starting from above. We know the multiplicity at negative 2 is 1, so we're going straight through. So we're going to come in straight through this 0. I've got to get down to that y-intercept, so I'm just going to kind of come on down. And once we hit this y-intercept, we have to turn to get back up. So I'm going to turn my graph up, and then I have to get to 2. The multiplicity at 2 was an m2, which means we're going to bounce. So as we come up to this y-intercept, remember it's a polynomial, so smooth curve. We're going to hit that 0, and it's going to bounce right back the same direction. And then there's no other points we have to hit, so I can put my arrow going down, maybe. So there's my down arrow. So we'll just make it an ugly arrow. And then over here, there's my up arrow. So if you can zoom out so you can see it all. All right, second one. We're doing the same thing, sketching the graph. So we need our in behavior, our zeros, which are our x-intercepts, and then our y-intercept. So this one here is in factored form because you can see you got parentheses everywhere. So when it's in factored form, the in behavior is a little more complicated, but the zeros are a little bit easier. So it's kind of a trade-off. All right, so to get our leading term, we still need that leading term in order to figure out our in behavior. Let me go ahead and get this labeled. All right, so for our in behavior, what we're going to do is we're going to pull the factor at the very front along with each x factor with its exponent in the parentheses. So one thing, if I look at this, I notice there are 2 x minus 3s. So I am going to rewrite this before I do anything as a quantity squared. So f of x is negative x times x minus 3 quantity squared times x plus 2. All right, in behavior. So I'm going to pull to get my leading term. Each factor, and that includes the factor out front, so that includes the negative x squared times, and then I go get the next variable part, which would be the x raised to its exponent 2. I go get the next one, which is another x raised to its exponent 1. So then we multiply these together. Remember your exponent rules, you add your exponents. So that is going to be a negative x to the 1 plus 2, 3 plus 1, 4. So this would be our leading term. So we can get the leading term without actually multiplying the whole polynomial itself. All right, so our right in behavior is based on the leading coefficient, which is negative. So it is going to be down. Our left in behavior is based on the degree. The degree is 4, which is even. Therefore, the left follows the right, so it is also down. All right, for our zeros or x-intercepts, we're setting our polynomial equal to 0. So I'm going to go get my polynomial, negative x times x minus 3 squared times x plus 2. So we're here. All right, it's already in factored form, so we just set each factor equal to 0. That negative 1 on the very front here, it's a non-variable factor, so we can just ignore it. So I'm setting x equal to 0. The exponent on that singular x is a 1, so m1. Scooch that over. Our second factor is x minus 3, set equal to 0, means x equals 3. Exponent is a 2, so m2. And finally, x plus 2 equals 0, so x equals negative 2. Exponent is a 1. So at 0, we're going straight through. At 3, we're going to bounce. And at negative 2, we're also going straight through. All right, y-intercept. Remember, for your y-intercept, you are plugging in 0 for x, so that would be f of 0. So if you need to do the algebra, do it. So I'm going to go get my polynomial, plugging in 0 for x. So we're going to have negative 0 times 0 minus 3 quantity squared times 0 plus 2. So one thing you want to be able to catch here is that common factor out front of x is going to zero out this entire thing, because we are going to take 0 and multiply it by everything. Well, 0 times anything is always 0. So our y-intercept is actually 0 as well. Our graph, I need an x and y axis. All right, so y-intercept is 0, so 0, 0. So right at the origin, we don't label that, so I'm just going to go ahead and put my closed circle. I need to hit 3. So I'm going to call this 3. And I need to hit negative 2. It's going to be on the left side. We'll go here. All right, my in behaviors were both down. So just kind of outside the graph. So I'll make sure I go the correct direction. All right, at negative 2, it was an M1. So we're coming straight up from below and we're going straight through it. So something like this. Well, once we get up here, it's a polynomial, so it has to make a smooth turn to get back to 0. Our multiplicity at 0 is an M1. So we're also going straight through. I'm coming down straight through. I got to turn in order to get back to 3. The multiplicity at 3 was an M2, so we're going to hit it and bounce. So I'm coming up to 3, hit it and bounce, so we turn and go right back down. And then I can put my arrows on there. So this is going to be the general shape of our graph. Now for your online homework, remember it's very, very picky. So you might need a couple of extra points to make sure that that maximum and that minimum are in the correct location. So what I would recommend for your online homework, anytime your graph is going to do something like this, go ahead and plug in -1 so you can get the correct height of that maximum. And then also go ahead and plug in 1 and 2 so you can figure out how far down you need to go. Because what actually might happen with this graph is it might be a little bit steeper like this. We don't know for sure. So to accurately plot it online, you need to make sure you get some extra test points in there like step 4 says. Get rid of all those extra lines. But if I have you hand draw a graph, that's just the general shape. So homework wise, make sure you plug in those extra points to get the correct heights of those maximums and minimums. All right, last thing, I believe, yes, because the rest are you tries. Use the intermediate value theorem to determine if the polynomial p of x has a real zero between the x values of 1 and 2. So the intermediate value theorem, I call this the IVT for short. The IVT is the YVT. It's all about y values. So in order to determine if a polynomial has a zero between given x values, what we want to do is calculate the y value at 1 and the y value at 2. And if those y values are different signs, then that means we do have to cross the x-axis, which would be giving us a real zero somewhere in between. So I need to calculate the y value at 1, so that means p of 1. So at x equals 1. Plugging in 1 for x. It's not -1, 1. Let me do a little algebra. 1 cubed is 1. 1 squared is 1 times 3 is 3. We have our -9 and our -13. All right, so 1 plus 3, 4. -9, -5. -13, -18. All right, so I've got my y value at 1. It said between 1 and 2, so now I need my y value at 2, so we're going to plug in 2 now. P of 2, 2 cubed plus 3 times 2 squared minus 9 times 2 minus 13. All right, 2 cubed is 8. 2 squared, 4 times 3, 12 minus 18, oops, minus 13. All right, 8 plus 12 is 20. 20 minus 18 is 2. 2 minus 13, -11. All right, so if you want a little visual to kind of go with this, what this is saying is when we are on the x value 1, we are at the y value -18. Let's scooch that down. So I don't know, I'm going to call that -18. So we're right here. When we are on the x value 2, we're on the y value -11, so here. So as far as a polynomial goes, they want to know, are we guaranteed to have a real zero? Well, a real zero means we have to cross the x-axis. So if I look at this polynomial, in order to get from one point to the other, I could just connect this way. We don't have enough information to know for sure, so we cannot guarantee, based on what we know, that this polynomial has a real zero between 1 and 2, because the y values did not change signs, meaning one positive and one negative. So, no, the polynomial is not guaranteed to have a real zero between x equals 1 and x equals 2. And if you were asked to give a reason, it would be since p P of 1 and P of 2 are the same signs, or you could say are both negative, or both less than 0. Anything along that line would work. So in order to guarantee there is a real 0 between two x values, your y values at those given x's have to change signs. And since ours did not change signs, we cannot guarantee that there is going to be a real 0 here. All right, the rest of these notes are you try it. So if you would like to try those on your own and then check them with the completed notes, go ahead and do so now.